Next, we talk about hierarchical clustering. Hierarchical clustering is to build a tree-based hierarchical taxonomy, although we call it a central grid from a set of documents on the taxonomy and Kubernetes. Central grid is Kubernetes like this is a tree structure. Like this, for example, we see an animal, we can divide it into two different clusters, two different groups, and each group you can further divide it into its subgroup, like this. So you can treat it like a tree-based hierarchical group. Okay, the approach is to do you can do a recursively apply any clustering. So for example, for this one, you can first generate two clusters for the whole data. So then you can divide the data into two. Okay? And then for each cluster you can apply here, you can use the k-means again. Then here we apply k4. So we can divide the cluster into the 4 subclusters. Okay, so here we can apply the same k-means class to do a further cluster. So it's all so this what here is that the recursive apply the k-means cluster here, and you can build such a hierarchical cluster. Okay. So we also call such approach is a top-down approach or divisive approach, because each time you build a tree from the top until down, and each time you just divide the group into a small subgroup. So we also call it a divisive hierarchical cluster or top-down cluster. Okay, any questions? No? Okay, so it's very simple, right? Just apply any for each different level to generate the virtual hierarchical cluster. Okay, here is show a central grid. Okay, so when we will start the hierarchical cluster, okay, here we can say when we build up the social tree-based clustering, then you can say, okay, I want only 4 clusters. Okay, you can choose by cutting the central grid at the desired level. Okay, for example here, I choose to cut here. So if you cut here, you will have how many clusters? 1, 2, 3, 4. You will have 4 clusters. First, okay, this is the second, third, and this is the fourth. Okay, so if you put the cutting at this level, for example here, then you will have 3 clusters, right? Okay, so you can use this to generate the number of clusters you want by just move your cutting line on the central grid. Okay. Any problems? Here is another approach called agglomerative clustering. We usually abbreviate as HAT, hierarchical agglomerative clustering. It's a bottom-up approach. So in this approach, we will start with each document in a separate cluster. So each document is a cluster itself. And then we will merge the closest cluster together. Each time we just merge 2 clusters. Okay, the merge from bottom to up. Okay, so it's called agglomerative clustering. Start with each document in a separate cluster. then repeatedly showing the closest pair of classes, and here there is one class. Okay, you see, so it's very different from the top-down approach. Like this, each time at first, at the start, each document is a cluster itself. And each time you just select the two closest classes will be merged. For example, maybe these two are closest, so you just merge them together. And the next time, maybe this cluster is the closest to this one, so you merge them. And the next time, maybe these two, you think they are closest, so you merge them. You just repeat to do the merge process until you build up. Each time you just until you build up the whole tree. All the data are merged together in the root code. Then you can start the HACR root. Okay, it's called bottom up. Okay, is this okay? Is it okay for you? Oh, I'll give you another example for you. Suppose I have some data here, like this. Okay, first, each data is a cluster itself. Okay, so we have 6 clusters, and the next we will choose. Just check all the 6 clusters and check which one is the nearest. For this one, the distance between the 2 clusters is the smallest, so we can form a group of the 2. And okay, next one maybe this group. And next one maybe this. Next one is this, and finally the 2 classes are merged together. So you can see the process. We merge. Each time we just merge 2 classes, and we can finally define and form a very big cluster. How do you know? You can see the such a hierarchical cluster. HAC, I will note in this way. And a very important issue is how to define the similarity between classes. You see, you have to how do you define the distance or similarity? You have to give some definition for it. There are 4 different approaches to give variance, many variance, to define the closest pair of classes. Okay, including completing, control, and averaging. Okay, first one is single limit. Single limit means I will adjust text for given 2 clusters. Given 2 clusters like this. Okay, there are 2 clusters, and each cluster has different number of several data inside it. Okay, then the single limit means, okay, I have to check all the data. All the data between the 2 classes. Okay, I check this one, and also this one. Here is another one. Okay, you see I have to calculate totally 6 distance, right? And which one is smallest? This one, right? From here to here, this is smallest. So I will reduce the smallest one as the distance between the two classes. It's called a single link. Here you see. I will simulate. Here I use the distance. Okay. So I will, in my case, I will change it to the minimum. The minimum distance between the x and the y. X belongs to the I cluster, y belongs to the z cluster. So it's a single link idea. Okay, any problem? Okay, here is an example shown here. A single link such an approach is usually generate a very, first you choose the two, next, third, fourth, and then the next will be like this. Because you see the two classes is their distance is the distance here rather than this one, right? So the algorithm based on single link, it will merge the two classes. Okay, it looks not very good. Okay. The next is a complete link. The complete link is use the minimum similarity. So here I use the case again. For the minimum, for the complete link, I will choose which one? I will choose the largest distance as the cluster distance. So I will choose this one. This distance will be chosen because it's the largest between the two pair of clusters. Okay, so they are chosen as the cluster distance. It's what we call the complete link. Okay, so for complete link, it will generate a different result. Here you see, okay, the first, second, third, fourth, and who will be the next one? Yeah, the up and down, right? This one. Okay, it generates a different result. Okay, so it's the final. Any problem? Okay, here I just here is a computational complexity, and basically the HAC method need to compute the whole similarity, the all pairs of similarity. Also, the complexity is really high. Usually we will take n to a third order, so it usually take a lot of time if your n is very large. So I will suggest don't use the HAC if you are handling very big data. The data number is really huge. The order is n to a 3. N to a third. That's very big. Compared with the k-means is just how many? K-means is KNN, right? K is usually maybe just 10 cluster number. N is usually maybe 100, maybe 100 dimensions, not 100 dimensions. How about your N? N is usually maybe, suppose, 10 to the 6, 1 million. So the order for this case is very, very big. So don't use HAC to do the hierarchical process. I would suggest you to use the top-down. Use the two-level top-down method. It's better. Don't use the bottom-up. It's not a very good tool to deal with the big data. Okay? The order, you see the order is very, very huge. Okay, the next one. The next one major is the average. So average, based on the mean, it's very, very clear. Chih-Yi method. Here we have 6, for the 2 groups, we have 6 distance, right? We just take the also, not only 6, we also compute the distance in between, also in between here. So we will totally have, nine distance. Then we figure the average distance. The trick is at the average, the distance between 2 centroids and between 2 clusters. Okay? So it will take more time to do the computation. Okay, but the result is better. Okay. Any problem for this measure of the cluster, for the HAC cluster? Okay, finally we will talk about what's the good measure, a good evaluation for the cluster algorithm. Okay, so remember, recall our main idea. We hope the intra-class, that is the all data in the same class have to be very similar, and the inter-class, the data in different classes should be very different. Okay, so we have to take care about intra-class and inter-class. We can measure the two, measure from the two aspects to evaluate the cluster is good or not. Okay, so the quality measure to find the is good or not, we usually to assess the clustering problem, we will use the ground truth. In our training, we don't use the ground truth for clustering because it's unsupervised learning, right? So we don't use the ground truth. But for evaluation, we have to know the correct answer before, so that we can make evaluation, right? So here we require the label data to do the evaluation. But remember, in training process, we don't use the ground truth data, we don't use the label information. Okay, first we introduce the purity. Purity means the definition here. And I give you an example. Suppose we have built a 3 clusters for this data. Okay, 3 clusters, and we just treat the first cluster. We want to calculate the purity for each cluster. Okay, we take the first one, the first cluster. The first cluster is purity. How to calculate purity? You can say like this. There are totally 6 points, and who is the majority? The base point, right? Base point is the dominant. Okay, so we can treat this cluster is belong to the rate cluster. Okay, then we just count. Totally there are 6 points, and 5 belong to the correct one. For the purity, okay, 5, 6. And how about the second? The second cluster. The second cluster, the blue points are dominant, right? Only 3 is at the blue cluster. So in purity it will be 4 to the 6. 4, 6. And for the third, very clearly, we just follow the same method. Calculate its purity is 3, 6. Okay, any problem? It's a very simple technique. And here we don't need to use the ground truth. It's a purity. But sometimes, if you add the label information inside it, you can make a more precise purity. For example, maybe the special cluster, it will make the evaluation more complicated, but the evaluation may be more reasonable. There's another evaluation metric called the range index measure. Okay, in the range index measure, okay, you will generate a table and use the table to calculate your index. Use the index of whether your index is higher, means your clustering result is good, is better. And how to calculate, how to generate such a table. Okay, basically you will have here you will use the label information, the ground truth. So the same class in the ground truth here, and if in your algorithm, in your clustering algorithm, you can put all the same data in all the same class in the same cluster. Then you count how many data you put into the cluster. They put into the same cluster, and they all belong to the same class. Yeah. And but some data, if in your algorithm you put the same data, if you put the same data into different clusters, but in ground truth they belong to the same class, so they are wrong. Here. And also wrong here. This means you put the same data, and you put this data into the same cluster. But in ground truth, they should belong to different classes. So they also fail. And here is the data may belong to different classes in your algorithm. And in ground truth, they also belong to different classes. Okay, so here, the total number divided by okay, all the correct one is here. The data are the correct. The number of correct data, and then divided by it. So you can calculate your rank index. Okay, any problem? So the rank index, the calculation is very simple. A, B, C, D is your denominator, and your A and B is your numerator. Okay, so just follow it. A, B, C, D, calculate all together. Sum all the same as your denominator, and the numerator is A and B. It's called a range index. And some researchers also use the precision and recall or F measure to calculate it. Okay, have I told you about the precision recall before? No? In previous, in that semester, in that year, right? Okay, so in this year, I haven't told you, right? Okay, so precision recall is just a very similar idea, and I will tell you how to do it later.